Hi everyone, we're on section 9.5 now, and I've made it now to the just an hour south of Paris in a beautiful town called Fontainebleau, and there's a big jazz festival here at the moment. But right now we got to learn about alkynes. So let's get to it. Last quarter I showed you a little bit about alkyne reduction. Reduction is thought of as adding hydrogen or removing oxygen. And of course, you know, oxidation is adding oxygen or maybe losing hydrogen. So this is a reduction series going from the most oxidized form, the alkyne, to less oxidized or more reduced, and then even more reduced down here with alkanes. So if we think of reduction as adding hydrogen, we can literally add hydrogen molecules. So the best way to do reduction is hydrogenation. So hydrogenation is where you take hydrogen molecules and you add them to the pi bonds. So the pi bonds grab these hydrogens, and you need two hydrogens, one for here and one for here, to get to the alkene. And then if you want to do that again, you just add more hydrogen. So excess hydrogen over some kind of catalyst, usually a metal like platinum or palladium is used here. So hydrogen with platinum or palladium. Now if you want to stop it in between, it's rather difficult to do that because the pi bonds love reacting with hydrogen. So in order to stop it halfway, there's two ways to do that we're going to learn. One is you can poison the surface. So if you look down here, here's that palladium or platinum surface, all these metal atoms here. Hydrogen will absorb onto there, and then your alkene will come and the hydrogen will get added. And that's why we end up with a cis alkene here, because those hydrogens are on the metal surface and they're adding together at the same time. Well, if we want to stop it at the alkene, then we don't want this to be very reactive. We only want it to be partially reactive. So the thing you can use to reduce the reactivity is something called Lindlar's catalyst. And that's usually some kind of lead sulfate material. We call it a poison. It poisons the surface, so it's only semi-reactive. So that's a good way to stop it at the alkene. If you want to stop it at a trans alkene instead of a cis alkene, if you want to stop it at the trans alkene instead of the cis alkene, you'll have to go through a totally different mechanism because, of course, using this method means you're always going to add hydrogen same side. So in order to get opposite side addition, so here are the hydrogens here, they're on opposite sides, you're going to need to have a totally different reagent system. Of course, once you get the alkene, it doesn't matter how you get to here. You can have a cis or a trans, just add hydrogen again. So to reduce an alkene, so here's the alkenes, you just need hydrogen with platinum or palladium. And only platinum is shown in this diagram. To fully reduce an alkyne, where you're way over here, you have to go all the way through. So I'm going to use this middle road here, excess H2. And usually we like to say excess just to make it clear that you don't mean to stop halfway. Which reagents partially reduce the alkyne and we form cis alkene, so that's going to be H2 on Lindlar's catalyst. And you can just write Lindlar. It's sort of a combination of a lot of different reagents. Partially reducing the alkyne to trans alkene would be sodium or lithium sometimes, comma, a solvent of cold ammonia liquid. This is usually at negative 30 degrees Celsius for ammonia to be a liquid. Normally ammonia is a gas at room temperature. Now these reactions are called hydrogenation, and maybe you know a little bit about partially hydrogenated oils. That's a very common product in a lot of our processed food these days. The reason why we use partially hydrogenated oils is because a lot of oils like olive oil, for example, have a lot of double bonds. So they have these long hydrocarbon chains with double bonds in them. We call them polyunsaturated fats. And the reason why they're liquid is because of all those double bonds. It turns out because those double bonds are cis double bonds, that forms a lot of kinks in that chain of fat. And so that makes them not able to stack or form intermolecular forces as well as if they were trans or if they were saturated. Now, saturated fats, we know, cause atherosclerosis and lead to heart attacks and things like that. That's why people limit their consumption of fats like lard and animal fats. But saturated fats are much more shelf stable than oils. If you notice, sometimes oils, really old oil sitting around, gets rancid over time. So one way that manufacturers like to try to preserve food is to try to get partially to the saturated fat. So maybe you don't want to convert your oil totally to saturated, but you want to just go halfway or so. And then that enables you to gain some of the advantages of a saturated fat, which is shelf stability. So to partially hydrogenate your oils and your double bonds, you can use hydrogen on platinum or palladium, right? But in this process, sometimes you have isomerization as well. So not only are some of your cis double bonds turning into alkane, but you have some of your cis double bond, especially at high temperature, can turn into trans double bonds. And then that's when you get trans fats. So a lot of partially hydrogenated fats actually contain trans fats as well. So that's good for you to know just as a consumer. So here we talked about that surface, hydrogen molecules on that surface, then the alkenes or alkynes can come on top, sort of like a helicopter, and then you've got the hydrogens adding same side. Now with the trans alkene, we see that you can't have that kind of a mechanism, right? We don't want to have a hydrogenation on platinum. So we've got to use these different reagents here. Sodium in liquid ammonia. Now, this is going to be a totally new kind of reaction that you've ever seen. This is going to have to do with something we call free radicals. Free radicals are unpaired electrons. They're very unstable. And the way that we get an unstable radical is by using something that has an unpaired electron. So sodium, usually we think of sodium plus ion, right? That means it lost its electron and it has a full shell. Sodium ions are pretty stable. That's why we don't really use them in a reaction. They're usually spectator ions floating around. But in this case, we're using sodium metal. This is the reduced form, and it's in group 1A, alkali metal. You learned it has one valence electron, the 3s1 electron. Well, we're using that electron right here. So we're going to use sodium with that one electron there. That's a free radical. Now with this guy, you know the weakest bond is this pi bond here. So one way that we think about a radical reaction is to think about this pi bond as breaking in half, like this, okay? So if you picture a pi bond breaking in half, sort of we've done this kind of thing with oxidative cleavage. So this is reduction though, and one way that we can do that is to break that bond. Now we've learned before, if you had a pair of electrons, you can move them like this with this kind of double-headed arrow. When we have single electrons, we tend to move them with a single barbed arrow. Okay, so this means one electron's being moved. This means two electrons are being moved. So what we want to show with this is homolytic, same side cleavage. So homolytic means you're breaking it so it turns out to be the same on both sides. Heterolytic is where they're different on both sides. So heterolytic would be if I moved both of these electrons to this carbon, or both of these electrons to that. That's heterolytic cleavage, breaking it unevenly. Homolytic is I'm breaking it evenly. I'm going to just chop it in half. Okay? So if I do that, then you can picture that I'm going to be left with only one pi bond now, and I'm going to have the one electron from this bond here and one electron from this bond over here. Okay, it looks like a little a bug or an alien here. Now the thing is, picture that there are orbitals here, right? This is sp2 hybridized. So here's an sp2 orbital and here's an sp2 orbital. Now it really looks like a bug. They repel each other. Remember Vesper theory that the electron clouds repel. So actually the way that these will prefer to form is in a trans orientation. So there's this. Okay? So this is more trans because they're on opposite side. And at this point, the sodium will pick one of these to pair with to lower its energy. So sodium, let's say it's going to join forces with this guy. And usually with free radicals, we like to show them joining together like that. Okay, so these two are joining together. And what's going to happen is they will become a lone pair. Okay, like that. Now as a lone pair, this is going to be negatively charged. And then that's when I have a strong base here. It's ready to pick up a proton. So the proton source I'm using is ammonia. So here's my liquid ammonia, NH3, and it's going to pick up a hydrogen and make amide ion as a conjugate base. All right, so now I'm running out of room here, but I think you guys can see what's going to happen here. I need another hydrogen here, and so I'm just going to repeat. Okay, wash, rinse, repeat. So we're going to take another sodium, add it to its electron to here, make a lone pair with a negative charge on this one, grab a hydrogen from another ammonia, and then you're going to have your two hydrogens that are opposite side. Again, let's look at where that opposite side orientation originated from. It originated from this initial step of having orbitals that are on opposite sides. And I think you know the reason why these prefer to be on opposite sides of each other, as well as the R groups prefer to be trans as well, is to reduce the steric hindrance. Okay, so it's a little bit messy, but here it is. I'm going to grab, I'm going to make a lone pair here and then grab a hydrogen and then finally get to my final product. So I'd like you to go ahead and write this out neatly, unlike mine, and go through it and see if you understand that. And then start learning these different pathways and include this as part of your reaction map. You can just do a little map with just these, just so you understand how to get from alkyne to cis-alkene, or alkyne to trans-alkene. What are the reagents you need? And then how do you go all the way down to the alkane, or from either of these get to the alkane?